So, okay, we're back.
Alrighty, let's finally get started. Sorry guys. Okay, so today we're going to talk about scaling blockchain and how we're going to make it so that cryptocurrencies, so that we can get Bitcoin to the point where everyone could be on the Bitcoin network and we'd still be able to have transactions. Okay, so I'm going to go over like naive solution, vertical scaling, and then Brian's going to take over for advanced vertical scaling and horizontal scaling. We'll explain what each of those things mean. But first off, let's get started. So to start off, I posed the question earlier, how do we measure current blockchains? So often right now what we do is we look at their ability to deal with increased transaction volume, and we look at like whether or not they can, or how many transactions per second. So TPS is something that we look at. And in December, the Bitcoin blockchain was about 149 gigabytes large. So that's pretty big. And not everyone wants to store that on their computer. So we need to consider how to make it easier for nodes to store that amount of data, especially since we want the following two properties. We want the volume of transactions to hopefully increase because we want more people to participate in the network. And then we want the block time to also decrease because we can't have people waiting like 10 minutes to get confirmation so that they can get their coffee, right? Does that make sense to everybody? Solid. So we want to consider these two things as we move forwards. Okay, so there's something called the scalability trilemma that we like to talk about in the blockchain space. Decentralization is defined as the system being able to run in a scenario where each participant only has access to this amount of resources, to some C amount of resources, as in like they have a regular laptop or they have like a small VPS. Scalability is defined to mean being able to process some number of transactions greater than C. So this is just like defining terms right now. And then security is defined as being secure against attackers with up to N resources. So those concepts should make sense. I will pose that you can only ever have two of those three things. But the problem is we'd like all three because we're talking about decentralization here. Does this make sense to everybody? Solid. Okay. So here we see this graph of like transaction size, and over time, so this isn't the most updated slide, but over time, you see that it's pretty standard, and we like have tried to keep it pretty constant. So the maximum number of transactions per second can be calculated like this. If we have an average of 546 bytes per transaction, so that's set, right? One transaction is going to take 546 bytes, and our current block size is 1 million bytes. Then the expected time to the next block is 10 minutes, or around 600 seconds for confirmation. Then we can compute the sustained maximum transaction volume in TPS, do some like canceling of units, and we should get something around 3.2 TPS. So this was from, this is around like when it was still pretty standard, but you can see that that was around 2016. If we keep going and we see this is a more updated slide, and this is like more recently at the bottom there, I don't know if you can see it, but that's like March, that's this month. And so I just want to remind you guys that we do have like a 1 megabyte block limit in Bitcoin. And so right now our average, which if you go to this website, and I included the thing on the top so you can go and look at that yourself, but right now where we're at, our average is about 0.831 megabytes. So in one block, we aren't actually filling up all of the transactions that we could be. But then in February, you remember there was that whole like peak and a whole bunch of people were buying up transactions. And at that point, our block size average was only about 1.054 megabytes. And so we've tried to keep it pretty constant, but even at the top, at the like very, very peak, it's only about like 1.07 megabytes. So even as the price might go up and there are many more holders of cryptocurrency, we try to keep the block size relatively stable because it becomes problematic if we go too far above 1 megabyte. However, it's okay if it drops and we don't have enough transactions to put into a block. So that's the point that I'd like to bring up with this graph. Does that make sense to everybody? And we'll explain why exactly it is that we try to respect that 1 megabyte limit. Yeah, go for it.
Once you have reached the 1 megabyte limit, would the miners refuse to take on additional transactions into the block to keep it at that size, or how should we mention that?
Yeah, so it's actually just because processing each transaction takes a little bit more time. So on average, for a miner to stay competitive, they might agree to like take on this amount of transactions and then publish that as a standard block. Does that make sense?
So they would refuse to take on additional transactions.
Yeah, so they collect the transactions that they're going to build into a block, and sometimes that amount varies a little bit, but they don't take on any more than that because we've agreed that this is how much composes a block.
Yeah, like the block is a finite size. You can't get more than this, right? You can't store more than you can store in the blocks, let's say. So they can fit as much as they want into this blocks. It's like this block, the block. And once the block fills up, you can't put anything else in it. So you have to stop there and then verify transaction. Try to verify this block before moving on to ongoing operations.
Do they have a monetary incentive to maximize the number of transactions?
Of course.
Yes.
Right. So a miner would want to take in as many because they could collect the transaction reward associated with each of the transactions. So the more transactions they process, the better for them. But we don't want them to be processing millions of transactions because then everybody's confirmation times are really slow because more transactions in a block means that to build a valid block, they need to do more work to confirm that valid block. So everybody has to wait longer. Okay, so this is just some TPS comparisons. So when you talk to somebody about somebody from Visa, for instance, or PayPal, anybody who is skeptic of Bitcoin and Ethereum and stuff like that, one thing they like to bring up is the transactions per second and how it compares to PayPal and Visa. So you can see those numbers. Bitcoin's not doing so hot. 3 transactions per second. On average, it used to be about 2.2 last year, and now our current TPS, as we just looked at, is a little bit lower because of our current dip in transactions. But still, it's nowhere near the number of transactions that PayPal, for instance, or Visa processes per second. And so this is one reason people like to point to when they say, oh yeah, Bitcoin's just never going to scale, because at maximum, theoretically, it's calculated to only ever max out at about 7 transactions per second, which is still not great compared to Visa and PayPal. So from there, people have gone and decided that, okay, so with the original Bitcoin consensus protocol, it's just not designed to work enormously. But we can build additional layers on top, or we can find other ways around this transactions per second limit, and that's what we're going to talk about today. Does that make sense? Solid. Okay. Okay, so to talk about current scalability, so we have 2 variables, right? Our transactions per second equation looks pretty simple. If we want to make our TPS comparable to Visa so that we can realize our dream of using Bitcoin to buy coffee, we have to increase our TPS. And we have 2 options. Either we increase the number of transactions, we increase the volume of transactions and our size of blocks grows bigger, or we decrease our block time, or the second thing on the bottom, block creation time. That makes sense to everybody? I didn't explain that super well. It's just a fraction. We can increase one or decrease the other. Okay, so we could either increase volume of transactions or decrease block time. And remember that the size of a transaction right now is about 546 bytes currently. Okay, so there are 3 ways traditionally that you can scale. Vertical scaling is called just adding more RAM, CPU power to each existing machine. So imagine just somehow upgrading all of the computers, or increasing block size. That's another example of vertical scaling that has been proposed is something called the Ghost protocol. Have you guys heard of that? No? Okay, so we'll talk about that a little bit more today. Ghost stands for greedy, heaviest observed subtree, something like that. But it's actually, the original proposed one was adopted in Ethereum, and then they branched off and started a different version, and now they're that's what they currently implement, and that's why Ethereum has a higher TPS. But we'll talk about that in a little bit. And then also payment channels are another way for vertical scaling. Horizontal scaling is the idea that you add more machines to the same computational power. So think sharding and side chains, which we'll also talk about. And then finally, you have diagonal scaling, which is just adding more powerful machines. So that's the idea of Plasma, Cosmos. I recognize those names might not mean a whole lot right now, but we'll come back to them. Okay. Any questions about different kinds of scaling there are? It's you can think of it as vertical is adding amping up each of them, each of the things you already have, or horizontal is just adding more, or diagonal is doing sort of both. Yeah.
These 3 options are all for the unpermissioned public blockchains, right? Because if you have permissioned blockchains, you have other possibilities to scale.
Yeah, exactly. Mm-hmm.
And also, these scaling techniques don't necessarily have to only apply to blockchain. This is for any sort of computing, like I said.
Okay, so we talk a little bit about the naive solution now. So then I guess like the natural question becomes, why don't we just increase the speed of blocks by decreasing the difficulty of proof of work? Does anybody have any ideas? So remember, proof of work is our consensus mechanism. It's like the amount of work you need to put into Bitcoin to make sure that like you verified that some miner did some work to prove stuff. Do you have an answer?
Would that compromise the security of the network?
How would it compromise security, though? It's easy to say that it would compromise security.
I'm not sure if I have a
That's okay.
answer, but
So it's good that you have that intuition, though. Does that make sense to everybody? Why, if we like reduce the amount of work you had to do to prove that you had done work, that is maybe not the best way to increase our speed. Sort of seems like we're compromising security in favor of just speed. Does that make sense? Just the intuition. You look skeptical.
The problem with that some computers are closer to good internet connections and
Yeah.
can guess it quicker than others. So if you make it too easy, then it will always be the same nodes to win the game.
Yeah. So then you also throw off, like, if somebody has more computing power, they might have more, like, they have a better chance of doing things, and that becomes problematic because then you have centralization, and that is something that we'd like to warn against. So proof of work, keeping it at the current difficulty, is sort of something that we have to maintain. We can't really play with that. So what else can we play with? Well, we can play with the time to broadcast the block. So for example, if instead I just, like, so if we go over why exactly increasing the speed of blocks and decreasing the difficulty of proof of work wouldn't be a good idea. So if you see here these two lines, that line represents the time to create a block. If the block, yes, what's up? Oh, okay. If our line just became shorter and we have, if our line just becomes shorter and we have a shorter time to create the block, you see how the time to propagate is still like the same amount of time? And so because that red line is the same like same amount of time, then the propagation time is just a higher ratio of block time. And that becomes, it means, like game theoretically, it means that it's more beneficial to withhold blocks because the time to propagate takes up a larger amount of time. And so you have more block orphaning because more people find solutions at the same time because it's a shorter amount of time to create that block. And then you mess up things like block reward halving, and you have more frequent forks, and there's more potential for double spends, and this becomes more problematic because there's a lot more, like it just makes everything, every attack that we've talked about so far, this sort of opens ourselves up to that possibility. Does that make sense? Because remember that a lot of the attacks we've talked about are based on this propagation time. And because the propagation time is such like a bigger part of the ratio, now that if there's like any opportunity to selfish mine or to do anything, then it's more beneficial to do it in this section where I have like a bigger ratio. Does it make sense? Cool. Okay. So, okay. So if we look at the cons of, yeah, so that was the basic idea. Now if we look at the cons, well, if we suddenly decided that we were going to implement this, then it would be less likely to be accepted in the blockchain community, specifically for those reasons that we just talked about. There's actually like a huge debate on like the block size, and there's a huge controversy over this. People have been arguing over it for years now. But it's less likely to be accepted than increasing block size because decreasing proof of work is, again, seen as like decreasing our security. And blocks, the proof of work thing is seen as a fundamental part of the Bitcoin protocol rather than just sort of a protective soft limit that you're putting on top of it. So we'd like to go with like an option that's more of a protective soft limit than rather changing like the fabric of what makes Bitcoin Bitcoin. So you have a question?
There was talk about changing the proof of work of blockchain, and then there was no consensus among the nodes. What was the solution that was discussed at the time, half a year ago?
Half a year ago, after they discussed changing proof of work?
Yeah.
They're not going to change it.
No, they didn't change it, but
Right.
there was a discussion in the community to change it to make it faster.
Yeah.
Was that what was being discussed?
Yeah, so they have this, like this discussion has been going on for quite a long time. I'm not sure if like this is the exact thing you're talking about, but perhaps we could speak further on it and you can point me to the Reddit thread that you were talking about. Yeah, so if we were to increase block size instead of mess with the proof of work, then we would be able to make the blockchain storage size increase faster, and it wouldn't make it faster to reach a safe number of confirmations. So do you see how with this, you would just have to wait 12 confirmations instead of 6. So right now, remember, our current block time for Bitcoin, we have to wait 6 confirmations for security. If we made this shorter, we would just have to wait 12 confirmations because the security is decreased. Does that make sense? People look a little confused. Okay, so the main idea here is just that if we make like changes, these obvious changes where like we would decrease proof of work, that's not going to work out so well because then we decrease security as well, and we change our game theoretical like table because then the miners are incentivized to do the wrong things. And if we do this where we increase the block size, then we might have cons like we now have to wait for more confirmations for equivalent security because now there are just like more information to go through. Does that make sense? Okay. Okay. And then, so now we're going to talk about vertical scaling by changing those parameters. So if we decrease the block creation time, this is the idea of Ghost Protocol, which was proposed by like Ethereum was the first people who started talking about it, and then they implemented like the Ghost Protocol in its purest form, and then they sort of changed that, and we'll talk a little bit about that. But so Ghost Protocol, the basic idea is you include orphan blocks called uncles. So does everybody remember what an orphan block is? Yeah? Okay. So if I have an orphan block, I'm just going to call it an uncle, and I'm going to keep track of the uncles up to 7 generations deep. So that means that up until 7 blocks ago, 7 like children, remember children are pointing forward, so if I go back 7 generations, then those uncles, I'm going to just keep a record of all of them. And uncles up until 7 generations deep get rewards, and if a miner includes the uncles, then they get an additional reward. So the reason we want to do that is because then we can increase the speed of blocks by decreasing the difficulty of proof of work, but we don't change the game tree because we don't change the choice table because instead of choosing the longest chain now, we're choosing the heaviest weighted chain, the heaviest weighted proof of work chain. Does that make sense? Because remember how we talked about the problem with decreasing difficulty of proof of work is now it's easier for people to create blocks, right? You're just going to have lots of people like proposing blocks. You're going to have way more orphan blocks. It's easier to promote attacks and stuff like that. So they took that idea and they sort of said, okay, well, let's not worry about that. But what we're going to do is decrease the difficulty of proof of work anyway, but then look at something other than the longest chain. So they did change like sort of a fundamental like detail that we had always sort of referred back to. Instead of the longest chain, now they look at the heaviest weighted proof of work chain, the difference being they include those orphan blocks called uncles. Okay, and then does that make sense to everybody? Just want to be clear on this. Okay, and so this also is supposed to decrease the incentive for pooled mining. One of the worries was that if you decrease the difficulty of proof of work, you'd have more incentive for centralized mining. But then if you are still taking the heaviest weighted proof of work and still rewarding people who come out with small blocks, and those uncles would get some reward, then it still works out for everybody. You look confused.
And this was implemented in Ethereum?
Yeah. Yeah, so the Ghost Protocol was implemented in Ethereum like quite a while ago, and then they sort of did like, originally the idea was to not just do 7 generations, but they did the whole history, and they just keep track of all the uncles. And then they decided that like that was just a little bit too much to deal with, so instead now they just do 7 generations. Yeah, and so the specific like game theory behind that is just with Ghost, if you can reduce transaction time and decrease incentive for pooled mining, specifically because we consider those orphan blocks that are 7 levels back, and we reward those stale blocks with 87.5%, and then any children that come off of those would get a smaller reward of like 12.5%. So they earn some money for being on the right chain, so they're still mining on the right chain. They just like, even though they put in the work, they didn't make the full, like they didn't become the accepted block. Okay, so this is the same sort of chart that we were looking at before, but this is specifically for Ethereum. So the average block time for Ethereum, remember how I said it had a better transactions per second, specifically because of this Ghost Protocol? So now the Ethereum has had 17-second block times at that like peak over there. Now it's about 14 because we're back into a lull in the blockchain space. So if we rough estimate that it takes like a 15-second block time between 17 and 14. If we take 15-second block time, then that's about 40 Ethereum blocks that match 60 minutes that the 6 Bitcoin blocks take. Does that calculation comparison make sense to everybody? 40 Ethereum blocks match 6 Bitcoin blocks. And it takes 6 Bitcoin blocks for one confirmation. Like we need to wait 6 blocks in Bitcoin. That means we have to wait 40 blocks in Ethereum. And 40 confirmations are much more secure than just 6 confirmations in the same amount of time, which is why even with Ghost Protocol, they've made it faster and proven that it's still more secure than like what they did in Bitcoin. Does that make sense? It's sort of kind of like a little bit of magical stuff. It's a lot of math that I'm throwing at you, and it might be like useful to go parse through it, but the broad strokes of it is if you can come up with a way to scale and prove that you're doing it securely and increase the transactions per second, there's a way to do it. It's just nobody has found like a way to really scale to this size where Visa and PayPal is at yet. What's it? It's impossible. Okay. Well, people do have that opinion, yes. But see, even with all this like success, Ethereum is still at only around 17 transactions per second. Okay, so we have another option. We can increase block size. Okay, so if we just increase the block size, we can fit more transactions into a single block. The general premise of that is like pretty easy. As long as you have all the miners agree to like include more transactions into a block, then you have lower transaction fees for users. Does that make sense to everybody? Why it would be lower transaction fees? Can I get somebody to explain that to me? All right, I will explain it. So you have lower transaction fees for users because one miner is going to verify all these like transactions. It's a bigger block. So when they verify one block, they include more transactions. And so if I'm somebody who's waiting to like get my transaction passed, I'm not competing with as many other people because more of us get accepted. It's like if you're applying to college and you have like, you apply to a college that has a higher acceptance rate, then like you have a better chance of getting in. You don't have to try as hard, I guess. This metaphor is bad. But does that make a little bit of sense? Like you don't have to pay as much to get the miner to be incentivized. Okay, solid. Okay. So larger blocks, the problem with larger blocks though, is that they take longer to propagate and even longer to validate. So other miners can only start working on a non-empty succeeding block once they've validated their current block. So larger blocks, having larger blocks, leads to a greater advantage for the authoring miner at finding the next block. Okay, so if we define some terms over here, hard fork, does everybody know what that is? A hard fork is something that's not backwards compatible, which means that like they've made a change and people who don't ratify to that change are like a little screwed. So they have like gone off completely in a different direction. So if they've decided to make like a hard change, then people who stay on the original one can't really like confirm transactions. They can't interact the same way as they did before with the people who decided to go the other way. Does that make sense? A soft fork is more the idea that they've made a small change, but it doesn't like ruin everything. And people who decide to not change can still interact with people like that. Make sense? Okay, so a hard fork, so this is a con, because if we increase the block size, we would have to hard fork. And that would mean that we have like a lot of unhappy people who split the community, and that's why people have been sort of like not super incentivized to do this. It lessens transaction fees, like we talked about earlier. This is bad if you're a miner, because you get to collect less reward. Then size increases very fast. So some people are worried about the size increase being a slippery slope. They say, like, where does the increase end? Which is valid. Slippery slope arguments are tricky, though. And then longer propagation times. We talked a little bit about this. Larger blocks, again, take longer to propagate and longer to validate. And so whichever miner gets their block accepted has a better chance at finding the next one. Does that make sense? Solid. And then large transaction attack. Oh, the one-time linear capacity increase. So the point is just that they feel like this is a temporary fix, and if you just increase the block size, then we're going to hit another maximum, another ceiling, and then you're going to have to increase the block size again, and people just don't want to think about that. And then large transaction attack is actually quite interesting. So Ethereum was DDoS attacked a little while ago. somebody like just generated a lot of dead accounts, and so they had a hard fork to change the client side of the software to remove accounts if they're dead. But the problem with that, it wasn't a malicious attack exactly, they were just like sort of pointing stuff out. But the enormous amount of accounts created, if you go back and look at the Ethereum history, like you have all these accounts and then suddenly you have like a huge bloated load of accounts, and then they finally like develop some software to delete some of those accounts, and then you come back and like you have the original active ones. But because there's that huge bloated part of history, there's more, if you reference any transactions in that bloated part, there's more for the miners to go through and dig, and so it takes longer. Does that make sense? And so if you can slow down everyone's transactions, that's kind of a problem as well. And that comes from increasing the block size. Okay,
I didn't
yeah.
understand how the increase of the block size is something to do with the accounts in Ethereum.
Okay, yeah. So if we increase like the amount of history that there is to parse through, it's the same sort of idea. If we just like, if there's more to look through, then people worry that it's bloating the history, and miners, in order to confirm stuff, they'll have to go through and like look for more things. There's just more to search through.
But that argument is also true for very old blockchains such as Bitcoin, where you just
Yeah.
have a very long chain.
Yeah, that's true. Yeah. Anyway. Okay. So then we talk about the decreasing the size of the transactions. So this is something that is like a little bit more popular with people. So have people heard of SegWit and recursive SNARKs? Any of those? That's okay. Okay. So we talk about SegWit. So segregated witness, or SegWit, the main idea is that digital signatures, does this look familiar to everybody? We did talk about this part in class. The digital signature up there for each transaction takes up a lot of space in each block. And so there's not really a reason they need to be there. They're only there because we need it once to verify that that block is correct. Remember, the digital signature is to confirm that this block is going to somebody who like is authorized, has the private key, matches the signature, stuff like that. Remember? Yes? Can I get a nod? Okay. So there's no reason it really needs to be there except for the first time when it's being verified. So we can remove them from the transaction data. That would like reduce the transaction size. Remember, it was like, what, 546 bytes? And if we can make it smaller, that's good. So segregated witness is the idea that instead of changing anything else, we're just going to reduce down the amount of the size of our transactions. So this is like the main idea is that we have like that script pub key. The signatures are kept in the script pub key. So we're going to move that to a separate add-on outside of the script pub key, and we're going to call that a segregated witness. So new nodes will see the new script pub keys missing like most of the information. They're going to know to look in the segregated witness. Old nodes are going to look at it and they're going to think the new script pub keys are crazy because there's no signature there. Anybody could steal the data, but they're going to say like the old nodes are going to be like, well, you know, it's not my Bitcoin. The transaction is still technically valid. I'm just going to pass. And so in that respect, this is why SegWit is a soft fork. Does that make sense? Because it's backwards compatible. Those like new nodes who decide to, or the old nodes that decide they don't want like any part of this crazy SegWit stuff, they're still like going to validate those transactions. They're just going to think it's crazy, but nodes, it doesn't really matter what nodes think, right? Okay, yeah. So the meaningless text will be considered like a little strange to the old nodes, but they'll confirm the transactions as valid, and that's the main point. SegWit is just interesting in that it abstracts away like the confirmation, the validation of this. So really, how it works is like, yeah, so even though there aren't any correct signatures in the transactions, really how it works is it'll just call segregated witness enabled miner will create a Merkle tree out of all the segregated witnesses instead of like creating a Merkle tree out of all the transactions. Do people remember what a Merkle tree is? I don't want to spend time like re-explaining this if it's okay. You don't have to like, it's not like crucial to understanding how SegWit works. It's just kind of fun. So the SegWit Merkle root then is included in the input field instead of your old Merkle root hash. And then the segregated witness Merkle root changes the transaction data of the Coinbase transaction. So it really fundamentally changes the block header and the makeup of the blockchain. So it like eventually gets integrated into the whole blockchain. But if none of that made any sense, that's okay. If you have questions, though, you can come ask. But yeah, so the pros and cons of segregated witness, and this has been debated a lot before it was adopted, but pros are that it's only a soft fork. It fixes transaction malleability, which means that it's still compatible with things like Lightning Network, which just came out, and then sidechains, and then it's not a slippery slope, right? It's a one-time fix, and it's not like I can just keep increasing some ceiling like I could do with block size. There are efficiency gains because it's less for each miner to parse through, and we do have a smaller size of the blockchain, so it's solving like several problems at once. Does everybody see how each of those points are like advantages? What's up? No, ask.
But has this been implemented both in Bitcoin and Ethereum? Bitcoin, or where was
do you
it
know?
This isn't a proposal for Ethereum at all. So
Yeah.
this has nothing to do with Ethereum.
It's just Bitcoin.
For Bitcoin, it's basically to, I guess, get rid of a field in the block so that they have more root stuff, more transactions.
Do you know if they have a similar one for Ethereum though? I don't think so.
I forget if they actually ratified segregated witness.
I think they did.
Because
Yeah.
They have to because I guess the Lightning Network works off of segregated.
Yeah. So they have SegWit, and yeah, it's like they have SegWit 2x now.
Basically, you get rid of a certain field in your block so that you can stuff more transactions.
Yeah.
Why not in Ethereum? Or did they have this from the very beginning in Ethereum, that they keep the public signature out of the
The
block?
ways that Ethereum and Bitcoin, their implementations are pretty different. So this was just a way to try to solve the block size debate in Bitcoin.
The block size debate has not been as large in the Ethereum community, I think. Okay, so if we go on to talk about the cons of segregated witness, it is a one-time linear capacity increase. What we mean by that is it's not like, does it make sense to everybody if I say a linear capacity increase? Like we are increasing it linear to the transaction size. Like we're just reducing the amount of space that one transaction takes up, but that's not increasing it like quadratically. It's not like having the size of it. Does that make sense? Okay. And it introduces a new type of DOS attack. So DOS, remember, stands for denial of service. Go fish with DDoS is interesting if you want to look into it. But then the con is also that the SegWit code is really complicated and really ugly. And there are other ways to solve malleability. Also, wallets have to incorporate SegWit, otherwise they don't work with nodes that do work with SegWit. Okay, does that sort of make sense? There are drawbacks and pros and cons. But in this case, the community decided that the pros outweigh the cons. Yeah? Okay. Solid. Okay, so now we get to talk about something fun. Do you guys know what ZK SNARKs are? Okay, so they stand for Zero Knowledge Succinct Non-Interactive Arguments of Knowledge. Wait, what? No, they stand for Succinct Non-Interactive Arguments. Okay, RKS stands for something else, and I have forgotten what that stands for. However, okay, so let's say this picture, I took this picture of Yoda in Hawaii, because I saw Yoda in Hawaii, and I was like, nobody's going to believe me, so I'm going to take a picture. And then Yoda only makes this face when he's in Hawaii, because that's his happy face, and nobody's ever seen Yoda make this face. So I took a picture, and then I want to message Yoda, and I want to become friends with Yoda, and I want to tell him I know where he is. But Yoda is a discrete character, so I can't just like broadcast to everybody, like I know exactly where he is. And if I send an email with like the full picture, somebody might hack that email and might find like out where Yoda is or something. So I'll just email Yoda a picture of this like very distinctive face he's making, his happy face, and he'll know that I definitely like have a picture of him and probably know where he is because I have this picture of him looking really happy. Does this make sense to everybody? So in this way, with so without having sent the whole picture and like given the whole solution, I can prove to Yoda something entirely different. Does that make sense? Okay, cool. Oops. Okay, so just that general premise is something that we'd like to establish, and then this is like the abstracted away idea. So we'd like to generate a proof that you can send a valid transaction from Alice to Bob. We want to include this proof and changes to the balance sheet instead of the transaction itself, because we don't want to include the transaction. So any machine in the network can verify that proof really, really quickly. Does that make sense? That general premise? So why this would be an improvement is because then miners can merely include a single proof that they validated all the other proofs and then and the changes to the state. And so that block becomes a lot smaller. That like verifying the blockchain is also a lot quicker. And the average transaction size, the average transaction size is the same, but the average proof size is a lot smaller because the miner has to go through less work. Does that make sense? We just make it easier for the miner to be able to verify something. Yeah? So this is the idea that's behind recursive SNARKS scalability, and the idea behind like ZK SNARKS in general isn't limited to blockchain. It's just a cryptography concept, and I'd like to emphasize that. Okay. So to come back to this slide, the drawbacks to this are that proofs can be very time-consuming to generate. It could take hours, and it requires trusted setup. Like, do you guys know what a trusted execution environment is? So this is actually something that's quite common. Like sometimes I think Samsung has phones that like have a TEE on it, and it's kind of cool. The idea is just that like we need to make sure that both parties participating in something have set up their program the same way, and how do we assure that it's set up the same way? So we need to have like a little black box on whatever device they're using. Like for example, between Yoda and me, I need to make sure, or Yoda would need to make sure that I like could only have taken this picture in one certain way, and he can only receive this picture in one certain way. And we just need to like be very sure of like how exactly I could have taken the picture and how exactly he could have received the picture in order for the proof to be valid. Does that make sense? Okay, cool. So yeah, so now we've come back to this. So the variables that we can play with are the size of blocks, size of transactions, block creation rate. We've talked about all of those, and even with all of those improvements, our Bitcoin transactions per second is still an abysmal 3.2. So we need to change something else. And so the solution has become to just not use the blockchain. There are other ways to do this and other ways to achieve this that Brian will talk about. And now we're going to break. Cool. We're at 3:07. Do you guys want to break? We'll take a vote. If you want to break, hands up, thumbs up. All right, Sally, you can have a break. Break for everyone.
But yeah, it'll be like
Everyone else has
just
to
a few
stay.
minutes. But yeah, I guess.
Do you need this?
Oh, I don't need this
Okay.
actually. I'm just gonna talk about it.
Sounds good.
Oh,
Let's chill.
okay. So I'll just take like 1 or 2 minutes, and then we'll talk about vertical scale. But
Can you take your water? I still have some water.
So it seems that link does not.
this one, it doesn't. Has anybody been able to access that? It's the what is it's not underscores. It's
Yeah, I
hyphen.
changed it to hyphens and it's still not.
Scale. Yeah, 1 second. So, is it not working?
Oh, thank you.
Does that work? Okay, cool. Let's resume. Okay, so in the third section, Gillian was talking about vertical scaling by changing certain block parameters so that you can make things a little bit more. You can make, I guess, things more quick or something like that. But we realized that it doesn't actually make too much of a difference. The gain, I guess the scalability gains that we get from changing parameters that deal with the blockchain don't actually contribute very much. So that's why we're here to talk about some off-chain scaling solutions that might be more beneficial. So if we recall back to what a Bitcoin transaction looks like, there are certain issues around Bitcoin payments currently, right? So we have this idea of long delays. So when I send a Bitcoin transactions, in order to be sure that my transaction's going to be finalized or is going to stay on the blockchain, I have to wait 6 confirmations or 6 more blocks before I get that like finality guarantee, right? And that 6 confirmations is 6 blocks, which on average takes around 10 minutes each. So I would have to wait around an hour for my transaction to be finalized. And so let's say if I was buying a coffee, I'd have to wait an hour for my like coffee purchase to actually go through, and by that time my coffee just goes cold, and that's not cool. There's also high fees. So this is back in like November of last year. The average transaction fee for something was around, for just a normal transaction was around like $6.75, which is insane to think about. It's actually different now, like as of right now, because there's like I guess less interest in this. This was back in like the craze, right? It's actually around 25 cents for like an average transaction. But I just wanted to show you that it was like $6 back in November, and so you don't want to be that one guy back in November who paid $6 in transaction fees for a $3 coffee. That's just not economical, right? So it means that it rules out like Bitcoin for purchases of like low value items. So it rules out like the possibility that Bitcoin can be used at like, let's say Daiso, right? The Daiso sells things for like $1.50, and if you're currently our transaction average transaction fee is around like 25 cents. That's like 1/6 of your purchase at Daiso. So that's not great. So how can we do this without having to deal with a blockchain? So do we have this idea that how do we ensure that, let's say Alice and Bob want to do business with each other, they want to send payments to each other, but they don't always want to like talk to this blockchain because it's inefficient and we have high fees and long delays. So that's the idea of using a private channel, or a payment channel actually. So what Alice and Bob do, I guess let me go back to the reason why we use a blockchain in the first place. So normally in the Bitcoin system or a blockchain system, sending transactions is like a peer-to-peer thing. Like Bitcoin is a peer-to-peer like I guess transaction system that allows 2 parties to send money to each other because they don't trust each other. In that sense, they don't necessarily trust each other. In this payment channel idea, let's say they're best buds and they can actually reliably trust each other and do business with each other, knowing that they won't cheat on any agreement. So the idea is that they can open a private balance sheet and say that, okay, they can update their balances offline, saying that they can operate on some sort of like credit, and once they're ready to actually finalize their changes, they'll actually publish that one final transaction back to the blockchain. So to settle that balance. So what it would look like is if they open a private balance sheet with, let's say Alice with 10 Bitcoin, Bob with 5, and somehow through a variety of transactions we get to some sort of other state where Alice ends up at 8 and Bob ends at 7, right? At that point, we see that there's like a mutual agreement to send 2 Bitcoin, and that's finalized. But it could be that this Alice pays 2 Bitcoin to Alice pays Bob 2 Bitcoin. It could be like 20 transactions of 0.1. Maybe like Bob is doing something for Alice 20 times and she pays them individually 20 times. But when we look at it in the blockchain, if we look at in the private balance sheet, we see that Alice pays him out 20 times. But when it's finally updated on the blockchain, we don't see that 20 transactions. We actually just see one big transaction, right? So the idea is Alice and Bob open this private balance sheet at the beginning, and they can do an arbitrary number of transactions back and forth, and when they're ready to say, like, when they're ready to, agree on these changes on whatever the final balance is, they'll close this private channel and settle this balance sheet. So normally, if we're doing this off-chain, meaning that they can technically just open up like a Google Sheets and like collaborate and saying, I'm gonna send you like this Bitcoin, and we'll settle our balances on Google Sheets, something like that. So that's pretty scalable, honestly, and that's pretty good, right? But this is contingent on the fact that Alice and Bob really trust each other. What if Alice all of a sudden one day goes back to the Google Sheets and says, I didn't want to send Bob all that money. I'm gonna change these updated balances to be that all the money that I originally had is, let's just change it back to like I have 10 and you have 0. And that's not really great. So we have this idea of we can't really trust the people that we're dealing with, and that's why blockchains are used. So how do we actually like do this, right? So we use really cool commitment schemes and advanced cryptography to actually be able to create like enforceable contracts between Alice and Bob so that they can't really cheat on each other, and so that we also maintain that private balance sheet functionality. So what these payment channels are actually called, they're called hash time locked bidirectional payment channels, or HTLCs, and in blockchain land we call them payment channels just for simplicity. But the idea, it's where you and another party that you're trying to do business with, you create this like balance sheet with them, and then you update that off chain so that it doesn't actually attribute to, let's say, more and more transaction fees, and you don't have to wait as long for these transactions to go through because they're technically instantaneous, right? They're just agreements to pay out and when they finalize this like balance sheet, right? So the way that I like to think about this, the analogy that I thought of is gambling at a casino, right? When you gamble at a casino, you don't actually gamble with your cold hard cash or your like credit card, debit card, whatever. You go to the casino and says, I want to buy X number of chips, right? And while you're at the casino, you just use these chips, or you settle these chip balances with other members in this casino. And when you're finally ready to cash out your balance using these chips, you go up to the casino teller and says, hi, I have this many chips, can I have my money back? And they'll be like, okay, sure. So that's the idea that I guess does that make sense? Right? You don't actually deal with like your cold hard cash at a casino. You actually just deal with the idea of tokens or chips. Yeah.
I think it's intuitive that you just set up the net between parties that trust one another. What I don't understand is how you solve the trust problem that you're creating with this by introducing this Bitcoin script between them.
Okay, so that's what I'm about to explain right now. Yeah. But yeah, so how do we actually what is like the commitment scheme that we really need to use so that even if Alice and Bob don't trust each other, how can they still be sure that that they have to cooperate, or how do we ensure that they have to cooperate? And yeah, so this is what a payment channel might look like, or not a payment channel, but when you open up a payment channel, let's say this is state 0, Alice opens up a payment channel with 10 Bitcoin in it, and Bob has 0 Bitcoin in this. So in this scenario, this is state 0. There's total of 10 Bitcoin locked up in liquidity in this payment channel, and so this section shows this is what Bob needs to have so that he can claim the funds in this payment channel that belong to him, and this is what Alice needs to claim the first payment, or to claim her amount on this payment channel. So I'll get into that in a bit, but the idea is that we have this secret key that they would share each other after they move on to a different state, meaning that it's moved on, or if somehow Alice wants to, let's say, prematurely withdraw her Bitcoin or something like that, she would actually need to provide her own signature, and then she has to wait 1,000 blocks. If Bob sees that, he'll know something's wrong, and he'll try to change something. I'll explain right here. So let's say we started off in this initial state 0, where we open up a payment channel with Alice and Bob, and somehow Alice sends 3 Bitcoin to Bob. So this updated balance sheet looks like Alice has 7, Bob has 3. But for some reason, Alice is a little bit greedy. She goes like, I kind of want my 10 Bitcoin back, but I didn't want to send Blob the 3 Bitcoin. So what she tries to do, what she needs to claim this 10 Bitcoin amount right here, what she needs to do is she needs to use Bob's signature, meaning Bob has to agree that we want to revert back to that state, and she needs her private private secret number so that she can actually claim that amount. But if she doesn't have Bob's signature, meaning Bob says, I have 3, I don't give you permission to take my 3 Bitcoin back, she'll sign off on this transaction saying that she wants to withdraw 10, but then in order for that to go through, she has to wait some larger number of blocks, like 1,000, so that this thing can go through. This is without Bob's permission. And so if Bob sees that she's trying to prematurely revert back to this 10 Bitcoin state, he can go like, wow, that really sucks. Alice is trying to cheat me. And so what he can do from there is he has Alice's signature now. All he has to do is to claim all the funds in this payment channel. All he has to do is use Alice's signature before this 10,000 block limit and say, this person tried to cheat me, so I'm just going to use her signature to withdraw the rest of the money in this payment channel. So this arbitrary wait time, this 1,000 block wait time, prevents someone from prematurely trying to revert back to a previous state that no one agrees on, or some of the participants don't agree on. Does that make any sense? If you have any question, I can try to clarify that right now.
What I don't understand is that B suddenly can use the secret key of A to block A from G,
okay.
Basically. How does he get the key of A? Because if he has it, then Bob can also cheat on A. He can always use the money to withdraw everything from the account, right?
So, okay. So the idea here in this example is, so Alice wants to get her 3 Bitcoin back from Bob. So what she needs to do is she needs to sign sign and verify that I want my money back. But in order to do that, I need to wait some sort of time amount before I can get my 10 Bitcoin back. But Bob sees that she's trying to do that. He sees her signature that, okay, she's trying to get her 10 Bitcoin back. And in that scenario, Bob can use her signature because she signed it. She already gave it out. He can use her signature to say that she's cheating on me and I'll take the money back from her. Right here. So in this scenario, we're in this state 1, not state 0 anymore. But if Alice tries to go back to this state, what she needs her signature and 1,000 blocks. Or if Bob says, yeah, you can revert back to this state, I don't mind, then he'll also give his permission to do so. He'll be like, I approve that this change was made, and we can settle on state 0 rather than state 1. The private number that they generate on each end is just used so that they know that they're dealing with the right person. As in this, you need the other party's signature, but you also need your own private number that you generate. And in the current state, you can't tell what each number's secret number is until you move on. These past histories don't really work, or they're not accounted for when you have this most updated one, because this is the most updated one should be the one that everyone in this payment channel agree with. Yeah.
So the signature of A and B change for each transaction, or do they
No.
So because once Alice gives out his signature, Bob can use it any time for manipulating them.
Technically, the signatures will differ every time, but for sake of simplicity, you can think of it as them signing an agreement saying that, yeah, we can go back to this, or I'm signing this because I want this amount. So it's just, the abstraction is we're signing some sort of paper document, and it's an idea of we're giving permission for that to happen. So like when you sign like a receipt at a point of sale service, you're basically letting the merchant receive your funds. You're letting them take your funds basically. So in the scenario where Alice tries to cheat on Bob, she needs to approve that she's trying to do this, and otherwise for Bob to be able to be okay with that change, he needs to approve it too. So that's the idea. And if Bob sees that Alice is trying to be a little bit shady, he can use Alice's signature that she provided because she's waiting for some arbitrary time so that she can receive these funds. If she provides that same signature showing that she's trying to cheat, then Bob can reclaim all the funds in this payment channel because someone's being malicious. So it's very similar to like the slashing mechanism where if you try to cheat, you lose all your money. Yeah. So that's just an arbitrary wait time. You need to give them some sort of time so that Bob has enough time to respond to this thing. So if Alice tries to revert back to the state 0 without Bob's approval, without Bob's signature, she shouldn't be able to immediately get that money because Bob wasn't able to, like, let's say, see that and say that, okay, I approve of this, this revert state change. If Bob sees that she's trying to withdraw money from the state, he'll know that, okay, she's trying to go to this state 0 without my permission, and I don't like that. And so I will use her signature that she provided to reclaim my funds before the 10,000 block limit gets hit. So it's a wait time for Bob to respond to something without his permission. And once he sees that, and he sees that, okay, I actually approve or I give permission for Alice to withdraw funds from this date, all he has to do is just sign off and say, this is my signature that I let you do this. So all Alice has to do is use Bob's signature because he gave permission for that to go through, and she'd be able to instantly get those funds. So she doesn't have to wait 1,000 blocks for the transaction to go through once she has Bob's permission. And without Bob's permission, she has to wait. Does that make any sense? Yeah. Sorry if that's a little bit confusing, but that was pretty technical. That's the basic idea of how payment channels work, where to enforce people not cheating in this payment channel, this is how you do that. Yeah.
Does Arbor use this mechanism? Ripple?
I don't think so because they're not a payment channel kind of system. They have a different consensus protocol, and the way that they send transactions is slightly different. Yeah. So the observation is that if someone tries to cheat, the other party, if they see that malicious behavior is going on, they can always override this and take the money in the deposit. Meaning, if Bob sees that Alice is trying to cheat on him, then he can slash her funds and take the money in the deposit because she's being malicious. And so this encourages Alice and Bob both to cooperate, meaning that this encourages both parties to cooperate, and so that this payment channel doesn't fall through. And this payment channel never even has to touch the blockchain except for the two endpoints back here where you open a balance sheet and you close this balance sheet. Does that make any sense? And so what that happens is it's really economical because you can send any number of payments between Alice and Bob. It just doesn't show up on the blockchain. And the only two transactions that do show up on the blockchain that are a little bit more heavy on the transaction fee side will be the opening for the balance sheet and the closing of the balance sheet. Does that make any sense? So those are the observations of what payment channels are. But we have two issues. When we create this payment channel, right, between Alice and Bob, we have a liquidity problem, meaning that this payment channel can deal with this number of Bitcoin, but we can't use up this we can't use this blockchain we can't use this Bitcoin in the payment channel until we finalize our balances, and unless we close it. And then So our funds are essentially locked up, and we can't use that money until we finalize this payment channel balance sheet. And another issue is that we see that this payment channel is opened up between two parties, in Alice and Bob. So it's easy for them to send transactions back and forth. But if, let's say, I wanted to do business with Charlie, do I have to open up another payment channel with him? So I have a lot of different branches of balance sheets. That would be really difficult to manage. So that's where the Lightning Network comes in. So the Lightning Network states that if we have a network of people who have payment channels open with each other, how can I do business with Charlie that, let's say, I only want to send, let's say I want to buy something off of him on free and for sale, and I don't really know him, but I don't necessarily want to open up one payment channel with him, because essentially what that would look like is I open up a payment channel with him, I send him the money, and then we close the payment channel. And that would be two transactions. Why couldn't I just send him the transaction on the blockchain directly, right? So what the Lightning Network enables is, if we have payment channels open to different parties, we can create this this path between Alice and Charlie, this payment channel path, that we don't need to directly know who Charlie is, or we don't directly need to have a payment channel open with him, but we can still facilitate this payment channel aspect, where I can send a promise to Bob saying, I'll pay out money if Charlie does something or sends back a message, and Bob knows Eve, and Eve will say promise to Eve saying that someone's going to pay me this amount, and I'll pay you this amount once Charlie responds. And Eve goes back to Charlie because she actually knows Charlie, and she says, okay, hey, there's people who want to do business with you, but you have to send me this thing first, and then I'll send you the required amount. And so what this enables is we have a path of payment channels where we don't have to directly interact with any particular person. And we do this securely by we modifying our constructions for our payment channels a little bit, and we use really cool crypto schemes to do this. It's a little bit out of scope of this class because the cryptography aspect is kind of advanced, but that's exactly what Joseph Poon and Thad were doing when they were defining the Bitcoin Lightning Network, so that they can get these off-chain instant payments, right? So what does this mean for scalability? So one, people can make payments instantly, provided that there's enough capital within a payment channel to do so. You don't have to wait for confirmation times, because essentially what you're doing is you're signing off on transactions saying that I approve of this update to this balance sheet, and it's basically an off-chain record saying this is the balance that I want to maintain. And so we don't have any blocks that we're dealing with. We're not waiting on anything. But once we have this updated state to the balance sheet, we know that this is the most updated record. And once you finalize the balance sheet, this is the final agreement between all parties that what the final account balances for each person will look like. And the transactions are fast because it's only dependent on the communication delay across the network, not like the mining aspect in any point. And two, you can use the Bitcoin blockchain as this arbiter to settle disputes. As in, if you know that someone was trying to cheat on you, and you can say, I want to close off this payment channel now and finalize whatever's on this balance sheet. We can do that using it's just an off-chain idea, and then once we want to settle back into reality, we publicize or we finalize this balance sheet or payment channel, and then we'll get this updated balance, right? So there's fewer transactions that get published to the blockchain in that sense. And I'll get back to you. But so instead of the 3 to 7 transactions per second that the Bitcoin can currently handle, the Lightning Network can potentially handle a lot more, that into the thousands range of transactions per second, because everything is kept off chain. If you think about it, like the naive example, if we kept everything on Google Sheets, that's pretty fast if everyone just agrees to different changes, right? And sending packets across this channel is very cheap and fast. It's really dependent on your internet connection. And so the only fees that you need to pay is the only fees that you need to pay is to open this payment channel with someone and to close that payment channel with someone. So it looks to everyone else as though there's only 2 transactions going on, but you and the other party get to conduct business however much you'd like. Yeah.
I was just wondering how much trust do we between the participants of the Lightning Network. So if everybody agrees to shut down the Lightning Network and to net it out in the blockchain, then everybody would have to give their keys to.
They don't have to give their keys. They would just they would need to they would need to provide signatures to show that I want to settle my balances. They just need to provide signatures, and all participants would just need to, or the participants within a payment channel would need to provide signatures for them to close this payment channel, to settle balances.
And then who would then send the instruction to the blockchain to book the net?
There's no one person sending out the instructions to the blockchain. It will be done through like the scripting process, so it's like automated, as in
Smart contract.
yeah. So essentially, you can technically do smart contracts on the Bitcoin blockchain. It's just not as sophisticated as what you can do in Ethereum. So that will allow you to like automate things, so you don't have one person who's open and closing payment channels with anyone or whatever. It's a smart contract or a script that does that for you. But we have some issues with the Lightning like scalability aspect. In order to do large amounts of business with people, you need large amounts of capital. You need that large liquidity within a payment channel, because your liquidity that you can send around to different parties is dependent on how much liquidity you have within a payment channel. Let's say we have 10 total Bitcoin locked into a payment channel. We can only send up to 10 Bitcoin between each other. We can't send like 11. We just don't have that access to that extra 1 Bitcoin in that payment channel, and we'd have to open up another one. And so there's a strong centralization force, meaning that if only people who have large amounts of capital or liquidity can afford to hold these payment channels for a very long time, and meaning that these larger payment channels get settled less often. And like the fewer capital, the lower amount of capital that you have like fewer nodes in the network, and so we get this like hub and spoke network topology. So we're relying on the same person to facilitate our transactions for us. Does that make any sense? Because if one person has a large amount of capital and they know a lot of people in this network, because people know that they have large amounts of capital that they can send back and forth, they always have to go do business with this one person. Like, you have to always do business with this one entity that has a lot of liquidity. And let's say one day he just all of a sudden decides, I don't want to send anything between anyone. So it breaks off this network. So we rely on this one central node, and that becomes a problem later on if one day he decides to do otherwise. And also one other thing is, even though, okay, the network has been, I guess, released in alpha for like 1 or 2 months now, but recently it got DDoSed. So it's still like a really insecure idea still, but it's definitely an idea that's still out there, that people are really trying to solve the scalability problem in blockchain and Bitcoin. So let's get a little bit into horizontal scaling. So we have 2 ideas in horizontal scaling. We have this idea of sharding. So sharding is the aspect of, if you remember back to horizontal scaling, instead of trying to add more like power to your existing system, you try to parallelize it and you create different aspects of your system so that it's a little bit faster. So sharding is the idea of creating separate shards of your blockchain so that you don't have to, I guess, do as much verification. What I mean by that is, normally if you do a transaction, let's say on the Ethereum network, we have to maintain state changes for every other person in the network and other contract addresses. And that becomes a really big thing to like keep track of, right? So the idea of sharding is, let's say we break off our big or like our blockchain in the Ethereum network into like partitions, into shards, into, let's say, this is America's Ethereum network as a shard, this is Europe's Ethereum network as a shard, and when someone in the American Ethereum network, they try to like send a transaction, all they have to do is verify the transaction within their shard, within their existing blockchain shard, and the Ethereum network would, the European network would do the same. And so you get like these shards that are acting in parallel, so you don't have to keep doing repeated work. And this is just an idea right now. It's trying to be implemented, but the difficult aspect about this idea is shards we don't have a way for shards to really communicate with each other, and that's what they're trying to fix. But sharding is the idea that you're trying to paralyze your blockchain by creating shards so that you have less things to work with and therefore can make things a little bit more fast. Sharding is actually a database idea. It came from like distributed databases. If you wanna make sure that your your big database can I guess have less things to update, you break it off into different database shards, and you try to make things more scalable in that sense. So that's the idea behind sharding, and that they're trying to do this in Ethereum, I think, or some people in like the Ethereum core are trying to implement sharding, but like I said, the communication between shards is kind of difficult at this point, but we might get there. It's still an idea that was proposed, but we also have what's called sidechain. So this idea is, let's say we can't really speed up the Bitcoin blockchain that much. So like, why not create multiple chains on the side that will have, let's say, that will have like different aspects or different wanted like parameters. So let's say if I wanted to, let's say I wanted to create like a side chain for, let's say, just buying like coffee, right? You can move it to like a faster but less secure blockchain just for purchasing like low value items. Something like that. That would be really nice because there's less things on the actual Bitcoin blockchain, and other things can still be pegged to it, and they can still do business in that sense. The cons is because you have sidechains that are distributed, like the existing blockchain becomes smaller and smaller, or not smaller, but like the miners on the network have to distribute themselves between different sidechains and the main chain. You lose security in the main chain because your hashing power has to be spread over amongst all the sidechains. The sidechains need some sort of security too, but yeah, the interesting idea is we can have sidechains for different aspects. Let's say this is from Blockstream, that they're also trying to experiment with sidechains, but you can have sidechains to do micropayments. You can do sidechains to do like just for different aspects and for different purposes, different types of purchases. So you can have like micropayments. You can do sidechains for like, let's say, real estate purchases, where maybe because they are more sensitive and they require more more capital, you want to wait like a longer time for things to be confirmed in the network. So that's what sidechains are like proposed to do. So you can have different like levels of security that you want, and certain sidechains will have support for that. The other aspect, the only like problem right now with sidechains is that if, let's say, we create like this sidechain with just you as a participant and you mine on it, does that mean like you can keep on mining like by yourself and accumulate a bunch of like currency in that sense? We don't know yet. So that's a problem that needs to be worked on. But these are just ideas that people have brought up for scalability issues. So scalability, so blockchains have this inherent scalability issue. If we remember back to one of the trilemma, the scalability trilemma, we have security, decentralization, and scalability, right? So we can only choose two of the three. most of the time we always want security, because if your security is compromised, your system is completely moot. No one would want to use your system because you don't provide any sort of like working security, right? So we get back to this trade-off between, do we want decentralization or do we want like scalability? Because in the Bitcoin network originally, the reason why we have this scalability issue is because you want this decentralization, you want to create this network of untrusted actors, right? And the only way that you can get these untrusted actors to work together is by making it difficult for these actors to do malicious things. And so that's one of the reasons why we have like a scalability issue in Bitcoin. You have this trade-off between, do we want efficiency or do we want like this anonymity or decentralization aspect. So for blockchains to be accepted on like a global scale, they need to be able to support what the global scale is, right? They need to be able to support the transaction volumes globally, or like what exists currently in our day and time. But how do we solve this issue without compromising like Bitcoin's like original vision of decentralization and trustless payments, right? So that becomes the fine line that do we go into a zone where we have less decentralization, which will be more scalable, or do we go into the zone where we have more decentralization, but we can't have that scalability aspect? So those are things to consider when people are considering like scalability solutions and ideas. Like the Lightning Network arguably is one where you can still maintain your decentralization and like trustless aspect. It becomes really cool. It's just because that's not on the blockchain anymore. You get this really cool way to do things. But those are just things to think about when you're thinking about scalability. So just like a recap of today's summary, we talked about how block size capacity increase can lead to increase in scalability, but there's not a big boost. We have talked about how segregated witness is a way that they proposed and they actually accepted for the Bitcoin network to provide, let's say, a scalability increase by modifying what a current block looks like and what a current transaction looks like, and they provide this hacky fix where they remove a certain field and allow for more room for transactions, something like that. We talked about the Lightning Network, which is a really interesting idea that's being worked on. It's still an experiment, but it can potentially lead to like orders of magnitudes of scalability for blockchains, and but we have this idea that it might run into centralization, which is a problem. And we talked about sidechains, which can be used for a variety of different like scenarios. So that's all we have for today. Does anybody have any questions? Yeah.
So if one listens to all these different solutions to achieve scalability in blockchain, it seems to me that we're still at a very rudimentary level of the development of this technology.
Yeah.
And at the blockchain conference yesterday in San Francisco, a number of people repeated that we're in the 1980s of the internet, so that we're still far away from seeing a really operational technical solution. My first question would be whether you agree with this, and the second would be if you compare blockchain to the technology of the internet in the 1980s, do you expect that there will be a one-size-fits-all solution like we had for the internet with the World Wide Web, or will we rather see in blockchain there would be a multitude of solutions depending on the need case that you would employ for the blockchain?
Yeah, so that's an interesting question. I think that right now, because we're still in like a really early stage, we just have we're still in an early stage of like, let's say, the blockchain ecosystem, where people are still trying to develop like really secure systems and really like working systems that benefit everyone. I think it's still in a very experimental stage. It's just that a lot of hype has been making like the technology kind of seem out of hand, or it's been amplifying what it actually is. Currently, I think it's still very experimental, and you can't really do a lot of things that we want today just yet. But once the technology is there, once we actually have working proofs that these like blockchain technologies or blockchain solutions can actually benefit our I guess global like problems, or try to solve these global problems, then that's when it gets interesting, where your technology is there, like the only thing is adoption, right? Right now, it's still in an experimental stage where people are still trying to figure out what's a good way to do blockchain, or what's a good way to design a blockchain. And I personally say that rather than a one-size-fit-all solution for blockchains, I like to see a lot of different ones, right? Like you have different blockchain designs for different situations and for different scenarios. And that makes more sense because it really depends on the use case that you're using blockchain for. You don't want to, I guess, compromise anything by just having a one like solution that fits all sort of like blockchain ideas or use
It's not
cases.
comparable to the internet and that the World Wide Web in the end is the one solution is applied for everybody with the HTTPS standard.
I think so. Yeah, like you might still want some sort of standardization, just so that it's everyone's on the same page. But you can still have a lot of different like ways to do things, I think, without having this one catch-all solution for everything. Like that becomes more general, or you can have a catch-all that becomes more specific depending on how people want to define it. So yeah, that's my take on things. Does anyone have a question? Okay. Thank you for coming today. We realize that it's spring break, but thank you for coming. We hope that we'll try to put this up on Piazza too, but hopefully that we can do. We'll try to post everything up on Piazza soon, so that you can, I guess, look more into scalability if you want to. But I think it's a pretty interesting aspect. We decided to give an optional lecture because, it's not really optional, it's optional attendance. But the homework for like next week will be to write something about scalability. Yeah. Thank you for coming.
Thank you for coming.